Right, so today we'll start a new topic, work, energy and power. Okay, so any questions on the previous things, circular motion, Newton laws of motion, kinematics? Any question? Okay, right. So these are basic things. We'll go quickly. So energy is the capacity to do work. And what is work? In terms of force and displacement. Work is what? F dot ds, right?
Yes, sir. Integral of F dot ds.
Yeah. So, and to do F dot ds, we have to know how to do dot product of two vectors, right? So, vector algebra, these things, if you already know these things, you know how to add vectors, right? Subtract,
Yes, sir.
triangle law, parallelogram law. After that, for multiplying vectors, you can multiply vectors in two ways. One is dot product, and another one is cross product. So, what are the difference? What is the major difference between these two?
Dot product means we'll get the product as a non-vector function.
Yeah, scalar. And cross product is a vector. Okay,
Yes,
and what about dividing vectors?
No, we can't divide no, sir.
Yeah, it's not defined.
We have to turn them into.
Yeah. So for multiplying two vectors, right, the dot product is also called scalar product because the resultant is a scalar. And dot product of two vectors A dot B is AB cos theta, with theta is the angle between them. And so this can be interpreted as A into B cos theta, and B cos theta is projection of B along the direction of A. This you know, right, from this right angle triangle.
Yes, sir.
So A dot B can be thought of as A into projection of B onto A, or it can also be thought of as A cos theta into B. So similarly, we can draw a triangle like this. So it's A cos theta is this one. So A dot B is A cos theta into B. Okay. So, and when the angle between A and B is 90 degrees, what is A dot B?
0.
So that can also be thought of as projection of B onto A is 0. Right? Similarly, projection of A onto B is 0. So,
yes, sir.
And unit vectors are denoted by cap.
Yes, sir.
And unit vectors icap, jcap, kcap. They are unit vectors along the x, y, and z directions of the Cartesian coordinates. And I dot I is 1 into cos 0, and cos 0 is 1. So similarly, j dot j and k dot k is 0. Okay. So what is the unique thing about this icap, jcap, and kcap vectors?
Sorry, what, sir?
What is unique about this icap, jcap, and kcap? So you can also have rcap, right? What is rcap? Unit vector
That is also. Yes, sir.
unit vector along radial direction. Similarly, theta cap, unit vector along the tangential direction. Okay. In polar coordinates, r theta coordinates. So what is the difference between r cap and I cap? Some sort of a major difference.
I don't know, sir.
Anywhere in space, the I cap vector is same. For example, if this is the region of x, y, z, okay, the I cap vector here is this way because this is x-axis, and here also it is this way, right? Here also it is this way. Okay, but what about r cap vector?
It can be anywhere, sir.
It can be here this way, here it will be this way, here it will be this way, right?
Yes, sir.
Okay, so r cap and also theta cap is perpendicular to this one. So r cap and theta cap vectors are a function of space. Both will change from point to point. But I cap is not like that. I cap, J cap, K cap, they are always same. Same in the sense it's a parallel transport. This is parallel to this one. Okay, but R cap, as you move from point to point in space, the direction will change. So any vector can be written in terms of its components. Ax I cap plus Ay J cap plus Ez K cap. Similarly, B and A dot B can be written in this form. This you know, right? Dot B can be in terms of components should be E dot B
Yes,
can
sir.
be as A into B into cos theta with theta the angle between them. It can also be written in terms of components, where Ax is the x component, Ay is the y component. So in terms of components, it's Cartesian components, Ax, Bx, Ay, By plus As and Bc. And A dot A is dot product vector with itself. So let's say A square plus A square plus A z square, and it's always greater than or equal to 0. It cannot be negative. And it's also the magnitude of the vector, the square root of this one. And A dot B is 0 means both are perpendicular. And what is the other possibility? A dot B 0 means A and B are perpendicular, right? Other than that, what is the other possibility?
0.
One of them
Both
can,
of them or any one of them.
any
Okay.
one of them can be 0. Okay, and work done. So right now we have understood the dot product of the vectors. So work done is defined as a dot product, F dot D. Okay, so it is F into D into angle between them cos theta. So it can be interpreted as F cos theta into D. The component of force along displacement into the displacement. Okay, and unit of force work done is same as unit of energy, which is joule. In terms of Newton and meter, it's Newton meter. Kinetic energy is the work done moving the mass from initial velocity to the final velocity. The initial velocity is 0, and the final velocity is v, and a constant force. The net force acting on a body or a mass is m into e. Okay, so this net force, if it is a variable force, then we have to get the work, we have to integrate it from x1 to x2. So m into a is a acceleration is v by dt. So and dx by dt we can write as v. So this is some sort of understanding of why a kinetic energy is defined as half mv square. Okay, because if you assume that there are no forms of energy and there is just a mass and some force acting on it, and because of that it is gaining some velocity. So the only energy this mass can have is kinetic energy, and that energy comes from the work done on it. So the net force acting on this energy. So from that you get an expression for kinetic energy calculation. We usually take this as granted, but if you don't have an understanding of why a kinetic energy is half mv square, this is a derivation. Okay.
Yes, sir.
And if the force is variable, then you have to define the force for a small displacement as f into dx, and then to get the total work done from moving from x1 to x2 or x initial to x final, we have to integrate this one between the limits x1 to x2. Okay, so if the force is plotted as a function of x, if it's a variable force, there will be some variation with x. So uniform force will be a straight line. Okay, parallel to x-axis. This is clear. This is a uniform force. Okay, and this is a variable force.
Yes, sir.
An interpretation of integral of some function is area under the curve. So the work done is area under this force versus x curve. So there is a work done. Right. And work energy theorem. So what is work energy theorem? Is it conservation of energy or something else?
Conservation of energy only, sir.
Yeah. So why is it called? It's not something. It's not given the same name. It's something else. A different name has been given as work energy conservation. Conservation of energy is initial work, initial energy. It's same as final total energy. Okay, but this is when there is no external force acting on it. But if there is some external force acting on it, if the work is done on the system, okay, that will go in increasing the energy work on system. Okay, so initial energy plus work done on the system, okay, that will be the final energy. And if you consider work done by the system, so it will be initial energy minus work done by the system. Is this clear? Again, when the
Yes,
system
sir.
doing work, it loses energy. So the final energy will be less than the initial energy. So work done, you have to be careful whether you see work done on the system or work done by the system. Okay, so this expression, which includes both energy and work, is called work energy theorem. If it is just this one, this part only, it's energy conservation. Okay, but if there is some external work done on the system, or if the system does some work, then we have to include the component, the term for the work done also. So this inclusion of this term makes it work energy. Okay.
Yes, sir.
And find the work done is integral f dx. Okay, I think we'll straight away go to PYQs. So this is a 2021, very recent. Just see whether you can answer this question. The particle is released from a height s from surface of the earth. At a certain height, its kinetic energy is 3 times its potential energy. The height from the surface of the earth and the speed of the particle at that instant are respectively. So it should be a simple question. You just have to use the definitions. So the first step is just write down whatever is there in your own words. The particle is released the height from the surface of the earth at a certain height. Okay, so this is earth. It is released from a certain height. So u equal to 0, and at a certain height, okay, its kinetic energy E is 3 times potential energy. And what is the potential energy here?
M must be, sir.
No, this is gravitational potential energy, right? So the gravitational potential is mgh, right?
Yes, sir. Here that H is yes, no.
Yeah,
okay, that is.
Yeah. First, we have to translate in our own terms. After that, we can relate to the problem. So from this, you have to get the height. So suppose this is h. Okay, and the initial height is say hi. Okay, so the kinetic energy at this point. Can you solve this problem? Just try. Got it?
No, sir.
Okay, I'll explain. See, this is the initial height hi. The initial velocity is 0, right? It's because it's released. So at particular height, say h, kinetic energy is 3 times the potential energy, right?
Yes, sir.
So to get the kinetic energy here, we have to use these 2 points. That is loss in potential energy from here to here. There will be this kinetic energy. Because here the kinetic energy is 0. Okay, and there is a gain in kinetic energy. Okay, that will be equal to the loss in potential energy here. That is mg hi minus h. This one
Yes,
is
sir.
okay. So from this I get the kinetic energy. Okay, and the potential energy at this point is mgh.
Yes, sir.
Okay, and he has given that k equal to 3u. This one you have to use. Okay, so that is hi is s. Okay, so s minus h equal to 3 times h. mg will cancel when I am equating these two. Okay, so s minus h equal to h, 3h. So it's 3u. Okay, so from this I'll get h as s by 4. Is this clear?
Yes, sir.
Okay. After you get h as s by 4, you have to find the speed here, right? So that speed is half mv square, which is equal to this kinetic energy. So half mv square equal to 3 times u. So 3 times u is mgh, right? So mg and h is s by 4. Okay, so from this I'll get it b as this one.
Fourth option.
Yeah. Done.
Yes, sir.
For this one, the energy required to break one bond of DNA is 10 to the minus 20. This is a very trivial question. You know how to do it, right?
Yes, sir. Divided by 1.6 and into 110 per minus
So
19.
don't do mistake here. Just write 1 electron volt equal to how many joules? 1.6 into 10 raised to minus
10
19
power minus 19.
minus 19 joules. So I have to find 10 raised to minus 20 joules. I have to convert to electron volts. So 1 electron volt is this much. So 10 raised to minus 20.
0.06 option B, yes, sir.
I have to divide, right?
Yes, sir.
It will be less than 1 electron volt. Is that correct? Because 1 electron volt is 10 raised to minus 19. This less than that, 10 raised to minus 20. So it should be less than that. It should be less than 1. That is the first thing you have to. Option B.
0.06.
Got it?
Yes, sir.
This one, the force.
25 joules, sir.
Okay. So it's 20 plus 30 by 2 into 1. So 50, yeah, 25 joules. So you did integration.
Yes, sir.
Okay, now another way to do it is if you plot this f versus y, it's a straight line graph, right? It's a
Yes, sir.
straight line graph, and at y equal to 0, it's 20, so it is 20 here. And the straight line, the value here will be 30 at y equal to 1. So this is a trapezium, okay, where the parallel sides are this value is 20, this value is 20, and this length is 30. Okay, so the area of this trapezium is average of these two, 20 plus 30 by 2, into this distance between the two parallel sides. Okay, so this way also you can find out. This one, just find v square. After that, you use v square equal to u square plus 2as, and this is known, that is 2 pi r. V square is 0.855 into 1 by 4 pi r is 6.4.
So acceleration v square by r only, no sir.
No, that is the centripetal acceleration. Here you have to find, you have to use the tangential motion.
The tangential acceleration bar. Okay.
You have to consider this radial part and the tangential part separately, but here it's only tangential part.
Radial acceleration also will be there, no sir.
No, that's not required. It's a constant acceleration that you can neglect.
It's constant tangential acceleration only, no sir.
Both. No, radial you can forget because you know projectile motion you can consider x motion and y motion separately, right? So similarly here also you can consider radial motion and tangential motion separately.
Okay.
Oh my god, no, I'm making some mistakes because it is in centimeter, no? It is for 10 to minus 2. So when it goes up, it will become 10 to 2.
So yes is 4 pi r, no sir.
Yeah, I made a mistake there. So it is 8. But I think here I put it correctly, no?
V square, how did you get us 8? I got 16 into 10 power minus 2, sir.
Yeah, 16 is the correct one. So the correct answer is 0.1, right? Did you get the final answer?
1 minute, sir. Yes, sir. 0.1. Wow.
Okay, so you have to make this quick calculation like pi is 3.14. So 2 times pi is around 6. Okay, and 6 times 8 is 48. So that is the approximation I made here. And 48 is approximately 50. Okay, so a little bit calculation is a bit lengthy. Is it clear?
Yes, sir.
So as far as the tangential motion is concerned, it's like a uniform acceleration motion. So
Yes, sir.
only that you are solving for this problem. But the radial part, it's v square by r. R is constant. Velocity is constantly increasing. That's a complicated motion, radial motion. That is not involved here. This is a particle moves from point this to this in a force. So work done by the force. This is very trivial. So what sort of a force is this? What do you need to say about this force?
Constant force, sir.
Yeah. So it's just F dot ds, right? So F dot delta S. Okay. So you can find delta S, right?
Yes, sir.
Final position minus initial position. So what is the answer?
C, sir, option.
Yeah. This one, two similar springs, P and Q, spring constants, this one. Okay, they are stretched by the same amount. Okay, Kc, then by same force case B, then work done by the springs, Okay, WP and WP are related as. Okay, this could be interesting question. Okay, so the first sentence is case A, and this is case B. So case A, they are stretched by the same force. So
First case, option D, yes, sir.
okay, so this can be also written as so the work done in the first case. So and Kp is greater, right? So Wp is less than Wq in case A.
What you have written on the expression WP equal to half kx square?
Yeah, work done on the spring will go in increasing the energy, right? Half Kx square,
Yes,
and this is Kp or spring
yes,
P,
sir.
and they are both are given the same force, no? That will be equal to K into X, Kx of both of them. Kp xp, that's also equal to Kq xq. And this thing I can written as uh, F square, that is K square x square by K. Okay, F is same for both of them. So Kp is greater, so Wp should be less in case A.
Second case alone, can you please explain again?
Case B, no? Case B, it's said the same. Oh, hold on. Okay, okay. This is actually case B. I made a mistake.
Huh.
This is case B. That's what I'm saying. How come I got the answer without? Okay, in the second case, WP should be less than. WP should be less. So this one. So case A, this should be the same amount, right? So XP equal to XQ. Let me call that X. So in that case,
Yes, sir.
WP is okay. X is same. So it's half Kp x square. So WP is greater, so Kp is greater, so WQ should be greater than WQ. I think I made a mistake. I should look at this one. So, okay, in case B, uh, P is less, okay, and in case A, P is greater.
In case B,
Hold on, answer is C only. This is the first one I have discussed is case. Okay, case A is clear.
yes, sir.
Okay. Case B, the thing is both the forces are constant, right? Same. Okay.
Yes, sir.
And work done is half kx square. This I can write down as k square x square by k. Kx square can be written as
Okay.
kx the whole square divided by k, and kx is same for both, which is equal to f. So it is f square by kp.
Yes, sir.
Okay, and kp is more, so wp will be less. In the
Yes,
second,
sir.
so wp is less. In the first case, wp will be more because half k x is same. So it depends on k. So wp will be opposite. So option C. This one. Oh, this is a trivial question. Okay, constant means initial speed is this one. So u is 10, and there will be some value of v. Okay, and acceleration is given. V is u plus 80. This acceleration, this actually is negative. V is negative. That negative value is this one, magnitude. So 0.1 by 10. So 0.01 is the acceleration. So 10 minus 0.01, or okay, instead of using, you have to use this one, v square equal to u square minus 2as, because s is known. U square is 10 square minus 20 is 0.01 into s is 10. Okay, this is 10, so 0.1, so 0.2, 100, 99.8. So half into m into v square. So this 1000 by 2, 500. I made some mistake. Okay. The force is okay, it's a uniform force, right?
Yes, sir.
What is this point x mean? Looks like a variable force.
Into, sir.
So this is unit, joule per meter. Joule is work done, no? So unit is fine, Newton only.
So non-uniform force.
Yeah, non-uniform, it's 0.1x. So we will integrate f dx, where f is 0.1x into dx. So work done is 0.1 x square by 2. That is 30 square minus 20 square by 2. 900 minus 400 is 500. So 250 is 25. Okay, and yeah, so then these things are not required. This energy conservation here. Initial energy is half m.
Half mv square minus half mu square equal to 25. I'm getting as 525, sir.
You have to find the kinetic energy.
Okay, retarding force means we have to add negative sign now, sir. And 475 Joule.
half mv square.
Okay.
Actually, u square minus v square, half m u square minus
V square minus U square only, no, sir.
No, there is loss, no retarding force. Then half m v square minus v square should be minus 25.
Ah, yes, sir. That's what I meant.
So half m is 10 into u square is 100, right? Plus 25.
Yeah. 475, no, sir. Minus 25.
Yeah, option E. Okay, right. Okay, this thing is a little bit unclear. The unit is joule per meter only because energy, the unit is joule. So joule per meter is actually Newton.
Okay.
This one, two particles emanating into move each velocity on collision of the particles, say to higher level after absorbing energy. If the final velocities are given into, then we must have. Okay.
We didn't discuss collision topic, sir.
Collision topic. There is only. It's based on two things. One is conservation of momentum. Okay. Other one is conservation of energy.
And head-on collision, purely elastic and inelastic.
Yeah.
Those stuff.
In elastic collision, there will be loss of energy. Okay, this looks complicated. Just a minute. Okay, so maybe collision will take next one. Okay, let's try some more problems.
Yes, sir.
Okay, to try this question, the person B, 50 kg rests on a string of length 1 meter. Okay, makes an angle 30 vertical. Other person B pushes him to swing on the other side at 53 degrees with vertical. So the work done by person B is get the answer.
Mhm.
You understood the question?
Yes, sir.
After drawing the question, reading the question, you have to make a small diagram like this. Otherwise, you'll make mistakes. So this is like a the situation, right? Initially, the thing is at a 37 degrees. The person and this person is pushing this thing so that it will go on the other side by 50 degrees. Okay, the length of that whatever is connecting the rope that will be same. Okay, so comparing the energy here and the energy here will be energy gained, right? Because more height is gained. So the energy gained is the gain in the potential energy, and that is the work done by this person who is pushing it, right? So you just have to get this height difference. Simple geometry problem. Or if you just get this height with respect to this reference, you can choose this as a reference point. Okay, and you have to choose upward direction as possible because Earth is downwards. Only with that convention you get mgh as gravitational energy. Because higher height means higher potential energy. That will be consistent with this consideration of positive direction as upward direction. Okay, so with this
Can
reference,
you please explain it again, sir? I can't understand.
no, for gravitational potential you can use a reference point, right?
What, sir?
For gravitational potential energy, it is mgh, no?
Yes, sir.
Which is from where?
From surface of the earth, from
But
ground.
you can also choose a reference point and choose reference from there also. So instead of choosing from Earth, that also you can do. I can also choose this point where the thing is hanging. So this is the origin of my height measurement coordinate. Okay, and this is the direction of the y-axis or whatever axis you can call. Okay, I'm saying this should be upwards because this point is some mg. Okay, with respect to this reference, the potential at this point is mg, say y2, and here let me call this y1, so mg y1. Okay, so if you use this as a positive direction, then mg y1, potential at this point is mg, say y1 is 2 meters, and this thing is mg y2, say 5 meters. So potential at this greater height is greater compared to the potential at the lower height. Okay, but suppose if we choose this as with positive direction of y-axis, then this thing will become negative, right? Minus and minus. So in that case, the potential at the higher point is lower than potential at the lower point. That is not true because if the Earth is downwards, the gravitational potential point at a higher point should be more compared to the gravitational potential at the lower point. Is that clear?
So that is okay, sir, but I don't understand that concept, sir. You said no.
Concept, which concept? Choosing this reference. No. Choosing the reference is clear.
Yes, sir.
Okay, and I have to choose the upward direction as positive.
Yes, sir, that is clear.
So, okay, then it's trivial. Whatever energy is here, and whatever energy is here, there's gain in energy. No?
Yes, sir.
That
Okay.
gain in energy is worked on all the system.
Yes, sir.
And system is this system of these two people. Okay, sorry, system of this person who's sitting on the swing. Okay,
Yes, sir.
so that work done has gone in increasing the energy. And mgh of this point, mgh of this point is this is the height. Okay, since this is the negative side, the height is minus L cos 53. Okay, and the height of this point is on the negative side, it's L cos 37, minus L cos 37, and there is one minus sign here, so that will make it plus L cos 37.
Yes, sir.
Okay, then so there are two things here. One, I can choose the reference for my gravitational potential energy. So I'm choosing this as the reference. Okay, reference point. From here, I'm going to measure the height. I'm saying the height should be measured in this upward direction only. Because Earth is downwards. Only if I measure height in this direction, mgh at this point is more than mgh at this point. Because potential at the higher point should be more. Because the body which is falling from this much height, when it reaches the ground, it will reach the higher velocity, no? And this person, when it reaches the ground, it will reach the lower velocity. So that means the kinetic energy of this thing is lower. Suppose I'm releasing from rest, u equal to 0 and u equal to 0 here also. So this thing when it reaches here, it has got more kinetic energy. That should have come from the potential of this point. So potential of this point should be lower because half m p square of this mass is more. Okay, that means the gravitational potential of this point is higher. This is the only thing you have to be careful. You have to choose upward direction as a positive direction. Reference I can choose any.
What are the cases that I have to choose that upward direction is positive, sir?
Always. See, whenever Earth is here, yeah,
Okay.
the potential energy at higher height is higher compared to the potential energy at lower height. No, potential means what? The capability to do what? So when this thing is falling from this much height, the velocity is freely falling. The velocity, the kinetic energy at this point is more for this fellow compared to this fellow, right? Okay, both are really released from rest.
Okay.
So the energy of this fellow is more than, because the energy of this fellow is more. At this point, the potential energy of these two, A and B, are same.
Yes, sir.
Okay, but the kinetic energy of this fellow falling of greater height is more. So that means the initial energy of this fellow is also more.
Yes, sir. Yes, sir.
So that is consistent if I assume the upward direction as positive. Suppose
Okay.
if
Yes,
the upward direction is positive, then this potential energy here will be negative. Okay, so that means the potential energy at the higher point is less than the potential at this lower point.
yes, sir.
Okay, this question number 2. Work done on by the friction force on a pencil in drawing a complete circle of radius 1. The circle of the pencil is mass with normal pressing force 5 Newton is. Question is clear? Work done will be work done against friction. So the friction force into the distance. Is this clear? Got the answer?
No, sir.
Okay, try.
Sir, friction will oppose the motion only, no, sir.
Yeah, so work done will be negative.
Okay. -5 joules, sir.
Yeah. See, it's a normal reaction. Why that when negligible mass? Just a minute. Got it? Your mic is off.
What, sir?
So,
Yes, sir.
okay, they're given is negligible mass, no? Why have they given that? See, the friction force is mu normal reaction. Okay,
Yes, sir.
and there is a pressing force of 5 Newton. And in addition to that, you can have some mass, right? mg. That's what's acting downward. This 5 Newton is applied force. Okay, 5 Newton. Suppose if you had mass, then the mg will be also be there. So then in the case, the normal reaction will be 5 plus this one. So to avoid this complication, they have neglected this mass. Is it clear? This n does not mean it's normal reaction. The symbol will not be correct. Okay, normal pressing force. So the pressing force is 5. Okay, in addition to the mass will be there, weight will be there, but here it's negligible. Is it clear?
If I write it on that wall, means then there won't be mg rule, no, sir.
Yeah, but have you said it? It's on the wall. They have not said it, no?
Okay, fine, sir.
Okay, this one. There's only one small catch. The velocity is increasing in time t1, but he's asking the work done in time t. So work done in time t is increasing the kinetic energy. It's half m.
Option D, yes, sir, from the dimensional analysis.
Half m v square.
Fourth option.
Yeah. Okay. Okay. So the thing is, if this time is more, okay. One way to get it is the thing is accelerate from 0 to v in time t1, right? So acceleration is v by t1. Okay, and kinetic energy is half mvt square. That is the acceleration e by t1 into t whole square. Okay, this one velocity time graph. Particular mass 2 kg moving in a straight line is shown in figure. Work done by all the forces.
Where, sir?
Here, this is the graph. Velocity versus time. Okay, so work done by all forces. So velocity is dropping down. So work done by all forces should be negative.
Minus 20 acceleration.
You don't have to find acceleration. Just the energy current, work energy theorem will do. There is a falling energy, right? E initial minus E final.
Yes, sir.
The kinetic energy is there. So this falling energy is half m.
V square.
M is 2. The V square minus U square is 20 square. 400 minus 396. Fine. What is the mistake? Finally 0. No? In 2 seconds. So it's 400. So minus 400 should be option B. Since this work done by all the forces are part of the system, so there is falling energy. Okay, by all the forces means external. So the work done is actually negative, so it's minus 400. Is it clear?
Yes, sir.
Okay, this one, the drop of mass in, its speed B compresses spring to a distance x. The speed is half. What is the value of the spring constant? This also reduces energy conservation. Got the answer?
What is the value of spring constant?
Yeah, half.
Says work done with spring force is half kx square only, no, sir?
Yeah, energy, spring energy. So half mv square should be equal to half kx square.
Yes, sir. Three mv square by 4 z square. Option A, sir.
Yeah, speed is decreased by half. Yeah, option A. Okay. This one.
Terminal velocity means it's a maximum velocity. It can't exceed further also.
Terminal velocity, see, velocity will keep on increasing if there is a acceleration, no?
Yes, sir.
Acceleration is same as force. So if force is there, net force is there, it will keep on accelerating. But as it keeps falling, there is a resistance force which keeps on increasing. The resistance force is pushed to the velocity. So at some stage when the velocity exceeds a limit, the downward pulling force because of the Earth's gravity and the upward resistance force because of the value of the velocity, both will become equal. After that, the net force acting on the body, which is the net of gravitational force downwards and the upward resistance force, both will become equal and it will be zero. So after that, it will be zero throughout because the velocity is same, so the resistance force is same, and gravitational force is same. After that particular point, the net force is zero, so it will keep uniform velocity after that point. Okay.
Yes, sir. The work done by the atmosphere. Greater than 100 mg. No.
Option B. Can I explain?
Yes, sir.
You have to draw a picture always. Initially, it's zero, no? Okay, and it's
Yes,
falling to
sir.
the height of 100 meters, where it attains its terminal velocity. After that, the velocity is not going to change. It's going to be constant. Okay, so greater than, okay, the work done by atmosphere during the, so we have to find the work done here, right? So the work done here, in this first part, I'm using the work done one. So that will be the initial energy is what? Mg into, compared to this one. So this
100.
loss of potential energy of 100, right? So loss in potential energy will be the gain in the kinetic energy, plus the work done by this drop on the atmosphere. Okay, so this is one equation. This equation is clear.
Yes, sir.
Okay, the second part, there is fall in gravitational potential energy, that is mg to 100. Okay, decreasing, that tells about the work done in the second part. There is no change in kinetic energy. This is the work energy theorem equation for the second part.
Yes, sir.
And this is a positive quantity, right? Because Vt square. So work done 2 is greater than work done 1. The work done in the first half is less compared to the work done in the second half.
So in terms of change in kinetic, it will be half mvt square equal to mg 100 plus work done by that opposing force now, sir.
Yeah, this is an equation.
That work done by upward thrust will come on that left side of that expression, sir.
So this is work done by the raindrop or whatever ball is falling. Okay. So it has gone in decreasing the energy of the system, right? So it's work done by the system.
Okay. Okay.
Kinetic energy gain here will be actually be less if there is no resistance. And that less kinetic energy plus the work done by it, that will give a, that will equate the loss in gravitational potential energy. In the second case, there is no gain in kinetic energy. Okay, so the total work done but the total loss in potential energy has gone in doing the work.
Okay.
Clear?
Yes, sir.
Okay, this one is spring constant 800 within resistance. The work done extended from 5 to 15 centimeters. This is a trivial question.
K is equal to F by X. Okay. And then
The work done has gone increasing the spring energy. The increase in spring energy will give the work done.
two 25.2
You have to find change in half kx square.
$16 Joule, sir. Yeah.
Option 2,
15 square will be 225 only, no, sir.
yeah.
No, sir, I am getting 160 Joule. Oh,
Initial energy is half m pi square. So 225 minus 25 is 200, right? So half k into 200.
oh, force constant value. Oh, sir. I thought it was force, sir. Yes, sir.
The spring constant k, 800 Newton per meter. Got the answer, no?
Yes, sir.
This one, the mass m is suspended from a weightless string. Horizontal force is equal to displacement. I will miss angle of 45 degrees. Initial direction is Got it? Your mic is off.
1 minute, sir. mg into 1 minus root 2.
Which option? Options are not.
1 minus root 2. No.
So the increase in gravitational potential is the work done. There is force into distance. Horizontal force, no. So we have to take the distance in the horizontal direction.
So 1 plus root 2. Option 1, sir.
Option 4.
So at the angle of it makes 45 degrees. At that only it has more energy, no sir. At that point only.
Yeah. So work done is increasing the energy. No, so I'm choosing this as a reference, and upward direction should be positive. Okay, so this mg minus n for this point, and is mg less than negative here. The height of this point is minus l. The height of this point is less negative. Okay, so the energy of this point is more. Okay, what makes sense is the gain in height. Okay, so the gain in height corresponds to gain in energy. So that gain in energy is the work done on it, the work done on the mass. Work done on the mass is force and resistance. Actually, F dot D. Okay, so you have to take the displacement component along the direction of the force. That is this distance. That is L by root 2. So if you do L by root 2, it will be the gain in potential energy. This is the gain in height. Okay. So is it clear?
So distance you have to take the horizontal distance only. No? So what did you take that? What you take?
The horizontal distance is only you have taken this L by root 2, no?
Yes sir, sine 45 degrees equal to opposite by
45,
L.
so it's
Okay.
equal.
Yes sir. Yes sir, got it.
Gain in height is this much. So you can think like that. This one. So yeah, again work energy theorem. So there is work done is there, friction force into the resistance, and energy, the kinetic energy is there, and then spring energy is there. Initially kinetic energy, finally spring energy, and there is work done. Okay, so work done by the system. So that thing will add to the final energy. Final energy will be less than the initial energy because of the work done by the system. So initial
So
energy,
work done equal to change in kinetic energy.
no, work done by what? Friction force, no. That you can find independently. Work done by the friction force. So the friction force will act for how much distance? By x distance. Okay, so the friction force will act for a x distance, that is x is compression of the spring. So 15 into x, that is the work done. Initial energy is half m 4 square. Final energy is half k x square. So there will be a quadratic equation in x. So you can solve for x. One of the value will be negative, that you can neglect. Should I give the solution?
So 5000 x square plus 15x plus 16 equal to 0. And how to solve it further?
Yeah, 5000 x square plus 15x minus 16 equal to 0. You got this equation?
Yes, so
Okay. After that, then you can do it. It's trivial only. You have to do it carefully. Yeah, b square 15 square minus 4 is that will become plus 4 AC. Okay, so how to take out square terms? So it will be 225. This 32 into 10 raised to 4. Okay, so 32 into 10 raised to, okay, here is the approximation is there. Okay, this first time we can neglect because it's 10 raised to 4, no? This is 225.
sir, but that friction force is opposite, no sir. Shouldn't I take negative sign for it?
Final
Minus
energy,
15x.
no. Final energy will be less, no, because of the dissipation. Final energy of the system will be less, no.
Okay.
Energy of the system will go down, no, because of the dissipation.
Yes, sir.
So the magnitude of the friction force, the work done should be added to the final energy. That's why you have to think physically, otherwise you'll make mistakes.
Oh, yes, sir.
Okay, again I made a second approximation. 32 I will consider as 36. It will become 6 into 10 square. That is 585 by 100. This will meet. Okay, this will be in meter. So it is 5.85. So it's approximately 5.5. Fortunately, there is nothing close to it. Otherwise, this approximation will not work. Is this clear?
Yes, sir.
You have to make quick approximations. Okay, one is neglecting this 225, and after that, considering this 32 as neglecting 225 means I have lost some value, no? And here also 32. So if you consider this as 36, I'm gaining some value. So this approximation compensating for the second approximation. If both approximations are in the same direction, then it's a problem. But this first approximation, second approximation are in the opposite direction, so they'll cancel a little bit. Okay, still I'm getting 5.85, so it is 5.5.
So if the work is done on the system, then it will be like initial energy plus work done equal to final energy.
Yes.
Okay, fine.
Always think like that. If work is done on the system, the energy of the system will go up. But here, when you have overcome the friction, the system will do some work.
Yes, sir.
So what you consider a system here is a block and the spring. Here,
Okay.
work is done by the block against the friction force. So its energy will go down.
Fine.
Okay. This is also a common sense question.
No, no, sir.
Okay, you can get an idea of acceleration, 100 meters in 10 seconds, no? So from this you get an acceleration. Suppose the initial energy is u, which is 0. Okay, so acceleration is once the final energy is known, v you can calculate. Okay.
They didn't give weight, no, sir.
Yeah, we have to assume 70 kg. It's just an estimate.
Okay.
Okay, so if you assume it's covering with uniform speed, then this is the speed. From that I can get an estimate of the kinetic energy. Okay, this one will stop with this one. This is the last question. Potential energy as a function of force between two atoms of diameter molecules approximately as a function of the distance between them. A and B are constant. It exists the distance between the atoms. The dissociation energy of the molecule is this one. Then D is. So it's like a mathematical problem. So we have to find D, where D is u equal to x equal to infinity. At x equal to infinity, what is the value of u?
0.
So you just have to find x u at equilibrium. So you have to find x of x at which it's at equilibrium. How do you find that x? Equilibrium is net force is 0, no?
Is suppose same.
And how is force related to u?
F dot x.
No. Force and potential energy. Gradient, no?
Sorry, what, sir?
Gradient force is du by dx minus negative gradient. F is minus du by dx.
Yes, sir.
Okay. So to find equilibrium means you have to put du by dx equal to 0.
Yes, sir.
So from that you will get the value of x at equilibrium.
Okay.
If you get value of x, you can find u at equilibrium. Then you get the answer.
Okay, sir.
You want to try?
Okay. 1 minute.
Got it?
X equilibrium
X at
2a
equilibrium.
by b power 1 by 6, sir.
Yeah, this one. So from that you can find u at equilibrium.
2A by B only, no sir. We got B by 2A.
I put minus 1 by 6.
Okay, fine. B square by 4A. Option
Yeah.
4.
Yeah.
Yes, sir.
Okay, we'll close now. So your laptop is working now?
No, sir. I have to change the RAM. This is RAM is done.
Okay, so right now what are you using?
Phone only, sir.
Okay, so the laptop is there with them.
Ah,
Okay, so the RAM you're putting is SSD RAM.
I don't know about it, sir.
Okay, what about the software? Windows Journal
Sir,
software.
I've asked my father to tell them to reinstall that software.
Okay, fine. So tonight is Shivratri. So
Yes, sir.
you'll be awake or what?
No, sir.
Okay, so tomorrow if I am tired, I will tell you. Otherwise, you'll have class.
Okay, okay, sir.
Okay, then bye.
Bye, sir. Thank you. So if you want rest, take rest, sir.
Okay, I'll send you message. Okay,
Thank you.
this thing you're practicing questions.
Yes, sir. Sunday only I took my ACOS notice from my grandma's home, sir.
See this thing. Uh, your NEET exam will be in the morning or afternoon. No, any one slot.
Afternoon 2 p.m., sir. This fixed for everyone. Only one, sir.
Fixed for everyone means.
For
No.
everyone, it is 2 p.m. only, sir.
Okay, so then you have to practice sitting for 3 hours in the afternoon. At sitting and studying in one place only for 3 hours. Okay, you get into that practice. Okay, right now you have this. Then you do one thing in the morning also. You sit for 3 hours and study without moving from your table. Okay, you have to get in that frame of mind. Otherwise, during exam, your mind will wander. You have to be mentally tough. Okay, so in the morning, you sit for 3 hours continuously one place, and evening also after the class, some 3 hours maybe whenever you find time. So get in this habit of sitting at one place for 3 hours and studying. Okay, you should not get up and all unless it's absolutely necessary. Just have a water bottle in front of you with you and get in the practice of sitting for 3 hours at one place and studying. Okay,
Yes, sir.
okay,
Yes,
then
sir.
bye.
I have to change my habit of sleeping in the afternoon, sir.
Yeah, yeah. You should sleep only once a day. Otherwise,
Yes, sir.
if the exam is 2 o'clock, then you can just take a power nap of 15 minutes or something. Uh, because for IIT exam, there are two exams: one paper in the morning, one paper in the afternoon. In between two papers, there is a gap of 2.5 hours. So you can have a lunch and rest for 15 minutes or something. Some people do that. Okay, but you have to stick to that timing. They already know the exam time, so they know when to take that nap. So like that you can plan, but you have to stick to the biological clock. Otherwise, it's a waste studying. Like you study and then you won't perform in the exam. Okay, so you
Yes,
have
sir.
to get in the habit. You have to set the biological clock also. So stop. If your exam is fixed for this thing afternoon, then you have to practice for that afternoon session. Okay, your mental alertness should peak at afternoon. Okay,
Yes, sir.
so right after it's not possible, then you have to gradually shift it, but you have to do it quickly because exam is coming. No.
Yes, sir. We probably in July or August. I
Okay.
think they say Corona will reach its peak in August. So there are chances of postponing NEET exam.
Yeah, right now you have to reduce that afternoon this thing just for taking nap of 15 minutes, maybe at 1 o'clock or something. After that, gradually shift it to 12 or something, and then you. And how do you know it's not there in the morning, the exam?
It is fixed, sir. Everyone do like that only.
Okay, all over India.
Yes, sir. All over India only.
Okay, then you do take a nap at 1 o'clock or something, and get in that habit.
Yes, sir. Okay, sir.
Okay, fine. Yeah, bye.
Bye, sir.